9.2 Systems of equations. So we know that we can solve a linear system by using either graphing, substitution, or elimination. And please note, a linear system of equations can either have 0, 1, or infinitely many solutions. So example 1, the number of solutions to the following linear system or system of equations depends on the values of a and b. So we have a value of a here and a value of b here. Okay, so let's go ahead and determine the values of a and b for which this system has, there's 3 parts to this: no solution, infinite number of solutions, and one solution. Okay, so let's do no solutions first. So in order for 2 lines to have no solutions, they have to have same slope, but a different y-intercept. Okay, so they have to be parallel and distinct. They have to be parallel, and one has to be up and one has to be down from one another. Okay, so we know that when we're in the Cartesian equation, so like standard form, we know that for equation 1, the slope is 4 over 1. Okay, for equation 2, the slope is b over 1. So in order to satisfy b, b has to equal 4. Okay, now we have to have a different y-intercept. So same slope, we can take on any a such that a does not equal 8. Okay, so there's the solution for number 1, no solutions. Okay, number 2, infinite. For infinitely many solutions, we have to have the same slope and the same y-intercept. Okay, so again, 1 and 2, equation 1 has a slope of 4 over 1. Equation 2 has a slope of b over 1. Therefore, our b equals 4. However, this time we want the same y-intercept, so a equals 8. By making b equals 4 and a equals 8, we are going to have infinitely many solutions. Okay, and 2. 1 solution. Okay, all that's required for 1 solution is a different slope. So if m equals 4 over 1, and the slope of the second equation equals b over 1, b cannot equal 4. Okay, and a can equal anything. And that's what we get in order to satisfy this linear system and to have 1 solution. Just take this as a little bit of a recall and a recap from our prior experience. Now let's really get into the vector portion. Okay, what we're going to focus on is elementary operations, and this is very similar to elimination. Okay, when we added and subtracted equations in order to solve for linear systems. Okay, so elementary operations used to create equivalent systems. So here are a couple of rules. We can multiply an equation by a non-zero constant, and we've seen that before when we did elimination. Okay, we can interchange any pair of equations. So we can write equation 1 first and then equation 2, or we can write equation 2 first and then equation 1, and it's going to mean the same thing. So that's all it means by interchanging different rows. Okay, and then we can add a non-zero multiple of 1 equation to a second equation, okay, to replace that second equation. So in other words, for elimination, we would add these 2 equations or subtract these 2 equations. Okay, so let's take a look at that now. Okay, so in order to simplify this, I actually don't write out the x's or y's. What I do is I keep these equations in the same order, and I write this using a matrix, okay? I just find it much easier. So we have 2, which is the coefficient of the x, 1, which is the coefficient of the y, the equal sign, and then -9. Okay, and we have 1, 2, and -6. So what we're going to basically do is we're only going to deal with the coefficients, and it's going to get a lot less confusing because there's a lot less like filler. Okay, so our goal is to get a 0 in this box right here. Okay, so what I'm going to do is I'm going to multiply this second row by 2. So the first row is going to stay the same, 2, 1, -9. And the second row is going to be 2 times 1 is here, 2 times 2, and 2 times -6. Okay. So now I'm going to do row 2 minus row 1. Okay, so I'm going to keep row 1 as it is, 2, 1, -9. And now I'm going to go 2 minus 2, which is 0, 4 minus 1, which is 3, and -12 minus -9, which is -12 plus 9, I get -3. Okay, and to simplify this, I'm going to divide this last row by 3, just so they're smaller numbers, okay? So I get 2, 1, -9. So we actually haven't even touched the first row, and 0, 1, 1. At this point, if we were to rewrite this matrix back into the Cartesian form of the lines, we would have 2x plus 1 equals -1y. And we would have, well, 0x, and that was the point. We would simply just have 1y equals 1. So now that we have y equals 1, what we can do is we can sub that back into the first equation. 2x plus 1 equals -9. 2x equals -10. X equals -5. I know where this went wrong. This is -3. Sorry, that's -1, and this is -1. So all that changes is 2x plus 1 equals -9. That doesn't change. It just changes when, I sub in this. So it's actually 2x minus 1 equals -9. When this comes over, it becomes plus 1, which creates -8. Sorry, our solution is -4. Okay, therefore, one point of intersection, and this point of intersection is -4, comma, -1. Okay, right now, you might be thinking to yourself, like, why do we have to do this entire, like, matricy or, like, matrix when we only have 2 unknowns, 2 equations? Because we've done this since grade 9, right? Or especially grade 10. So the reason why is because we're going to get used to it so that when we have 3 unknowns and 3 equations, that we're pros at it. We're going to determine whether this point, x equals -3, so this was a typo, -3, y equals 5, and z equals 6, is a solution to this following linear system. So we know that in either 2D or 3D, so r squared or r cubed, if we have 2 lines and they intersect, then both of them will share that common point. That means if we were to plug this point in, it would satisfy both equations. So let's go ahead and test equation 1. Okay, so just rewrite equation 1, and I'm going to sub in x equals -3, y equals 5, and z equals 6. Okay, so I get -6 plus 15 minus 30 equals -21. And let's just calculate this. Double check. Yep, -21 equals -21. What this means is that the point -3, 5, and 6 lies on equation 1. Okay, now let's test equation 2. So a lot of times I just rewrite the equation, okay, so that I can flow down. So -6y is 5 plus 6z is 6 equals 8. So -3 minus 30 plus 36 equals 8. Let's test this. -3 minus 30 plus 36 equals 3. I get 3. Does 3 equal 8? No, 3 does not equal 8. Okay, so we can say, therefore, negative 3, 5, 6 does not lie on equation 2. Therefore, this is not a solution to this linear system. Okay, what this looks like is, I'm just going to make this up, but negative 3, 5, and 6, if this is equation 1, and this is equation 2, then this point right here does indeed lie on equation 1 right here, but maybe it's just kind of like a little bit far away from equation 2. Maybe it's close, but the point is it lies on 1, but it doesn't lie on equation 2. So we have to talk about overall. And overall, this point does not satisfy both of these equations. Now what we're going to talk about is consistent and inconsistent. So a linear system that has one solution is consistent, or an infinite number of solutions is consistent. Okay, an inconsistent linear system that has no solutions. So whether or not they're skew or whether or not they just, they're parallel. So parallel or skew, okay, or consistent is one point of intersection or if they lay on top of each other. I'll just make that thick. Okay, so that's what we're looking for. So solve the following system of equations for x, y, and z using elementary operations. And again, I'm going to set my elementary operations up in the form of a matrix. Okay, so what you first want to do is make sure that all of the equations are in order. X, then y, then z, and then an equal sign, and then a constant. So what we can do is we can just rewrite this just with the coefficients. 1, negative 1, and 1, equal sign 1. 2, 1, negative 1, equal sign 11. 3, 1, 2, equal sign 12. Okay, so what we're trying to do in this case is we are trying to, so we have 3 equations, 3 unknowns. We're trying to get, to the best of our ability, zeros down in this corner. Okay, so what I'm going to do, the first step, I'm going to try to get this 3 to a 0, and I'm going to try to get this 2 to a 0. Okay, I'm only going to do one operation for row 2 and then one operation for row 3 at a time though, okay? So I'm going to take row 2 and I'm going to subtract double row 1. Okay, because then 2 minus 2 is going to be 0. Okay, so row 1's not going to change. So 2 minus 2 equals 0. 1 minus negative 2. So 1 minus negative 2 is 3. And we have negative 1 minus 2. I get negative 3. And then I get 11 minus 2, and I get 9. Okay? So now, similar, but row 3, I have a 3 here. So we're going to have to subtract 3 of row 1 so that we have a 3 minus 3 equals 0, right? That's the whole purpose of this. So row 3 minus 3 of row 1. Okay, so 1 minus negative 3. I get 4. It's like 1 plus 3. 2 minus 3. I get negative 1. And then 12 minus 3. I get 9. Okay, so it's working out pretty well so far. All I'm going to do in this step is I'm going to divide row 2 divided by 3, just so it's more simplified, okay? So I get 1, negative 1, 1, 1. Now I get 0, 1, negative 1, 3. 0, 4, negative 1, 9. Okay, so all I have left, remember, we're trying to get these 3 to zeros, if we can. Sometimes you won't be able to. And then that's going to look a little different. So what I'm going to do in this case is I'm going to subtract 4, so row 3 minus 4 of row 2. And the reason why I'm picking row 2 instead of row 1 is that row 2 has this 0 here. So we're going to go 0 minus 0, and we're still going to get a 0 in this place. Whereas if you subtracted row 1, you're going to get a number. You're going to get like -4 in this place. Okay, so I'm going to just rewrite equations 1 and 2, rows 1 and 2, I should say. And then we're going to deal with row 3. Minus 4, I get 0. Okay, and that's the whole point. And then I get -1 minus -4. So that's -1 plus 4. I get 3. And then I have 9 minus 12, which I get -3. So again, I'm just going to take row 3 and divide it by 3 just to simplify it. So now I have 1, -1, 1 for my first equation, my first row. I get 1, -1, 3, and I get, 1, -1. Okay, now here's the whole purpose of this. We have 0x, 0y, so this right here tells us that z equals -1. So that's done, okay? What this row tells us, because we have that 0 in there, is that y minus z equals 3, or in other words, y minus -1 equals 3, y plus 1 equals 3, bring that over, y equals 2. Okay, so we're actually able to build and solve for one unknown each time. Okay, and then we have x minus y plus z equals 1, or x minus y is 2 plus -1 equals 1. -2 minus 1 is -3. Bring that over, x equals 4. Okay, so therefore, the point of intersection is 4, 2, -1. Because what we did here is we used matrices, matrix operations, elementary operations, in order to take out two of the variables, in order to get the x and the y to 0, and then we're able to solve for the z. Sub it back into the one above it, able to solve for y. Then sub in the y and the z into the row or the equation above it, and then solve for x. This is an example of 3 equations, 3 unknowns. Okay, and because this one has a one point of intersection, we can say that this linear system is consistent. Okay, let's consider the following system of equations. X plus ky equals 4, and then kx plus 4y equals 8. So let's determine the values for k, which the system of equations has 0, 1, and infinite solutions. So usually what we're able to do is we're just able to find like multiples, right? 4 times 2 is 8. So then we'd have like 1 time, or 2 times 2 is 4, and then that would be 1 times 2 is 2. Okay, so that's what I would be looking at initially, but sometimes it's not always this easy. So if we have 1k and 4, and we have k, 4, and 8. Okay, so we said originally if k equals 2, then what happens is we have 1, 2, and 4. We have 2, 4, and 8. And these are multiples of times 2. Okay, therefore, infinite solutions. Infinite solutions. Okay, but it's not always this easy. So I'm going to show the complex way of solving for this, because to solve for one solutions or no solutions, it's much harder. Okay, so what we're going to do is I'm going to write out x plus ky equals 4. And I'm going to write out kx plus 4y equals 8. And just keep in mind, k is just some constant. So it's like a constant number. Okay, so what I'm going to do first is I'm going to multiply equation 1 by negative k. Okay, so I can do this in matrices, or I can do this set up kind of like an elimination. So I set this one up kind of like elimination just so you can see, since it's such a complex question. Okay, so we have negative kx minus k squared y equals negative 4k. Okay, and that's just multiplying every single term in the first equation by the constant negative k. Now let's just rewrite the second equation as it is, okay? So now what we can do is we can add these two equations together, because now what happens is negative kx plus kx cancel out. And then what do we have left over? So on this side, we can, because negative k squared plus 4 is difficult to write, we can actually just group these. So we can just write it as like our actual operations. So negative k squared, and then we would be doing plus 4 y's equals, and then negative 4k plus 8. Okay, so that is our equation right now. And all we did is multiply 1 by a constant and then added these equations. Okay, from here, what I'm going to do is I'm going to factor out this negative. So let's put the negative y at the beginning, and then what I have left is k squared minus 4. Then I'm going to factor out this negative 4, and what I have left is k minus 2. Okay, now I have a negative y. I'm going to factor k squared minus 4. So we have k plus 2, k minus 2. And that's going to equal negative 4, and then k minus 2 again. Okay, I'm going to simply divide both sides by negative 1, which negates these. Okay, so this is our equation. So there's 3 different cases, okay? So let's do when k equals negative 2 first. Okay, so when k equals negative 2, this is what we get. We get y, negative 2 plus 2, negative 2 minus 2, plus 4, negative 2 minus 2. So we get 0. Oops. 4, negative 4. Okay, so what we get here is 0y equals negative 16. All right, so what number can we sub in for y in order to have 0y equals negative 16? Well, nothing, because we know that 0 times any number is going to equal 0. So what we're going to do is we're going to take that k equals negative 2 and sub it back into the originals. So we have x minus 2y equals 4, and then we have minus 2x plus 4y equals 8. Okay, so right here what we have is 2 parallel lines. Therefore, no point of intersection when k equals negative 2. So now let's look at the same situation, but for k equals 2. Okay, so all I did was rewrite the equation. So now we're going to test when k equals 2. Okay, so let's go ahead and sub it in. Y, 2 plus 2, 2 minus 2 equals 4, 2 minus 2. So this is y for 0 equals 4, 2 minus 2 is 0. So we get 0y equals 0. Okay, so when does 0y equal 0? Well, for any number for y, any. Therefore, there's infinite solutions. Okay, that means that these equations lie on top of one another when k equals 2. So let's go ahead and solve for that. I'm just going to put in the corner here x plus 2y equals 4, and we kind of already saw this, and then we have 2x plus 4y equals 8. Okay, so when these two are the equations, there's going to be an infinite number of solutions. Now let's test when k does not equal plus or minus 2. So plus 2 and minus 2 worked out perfectly fine. Now let's test when k does not equal one of these beautiful solutions. Okay, so just out of common sense, if we have this equation right here, just from the original, what we're going to have, if we don't have plus or minus 2 in here, we're going to have some number y, so let's just call it ay, and it's just going to equal some number b. Okay, so when ay equals b, as long as y does not equal 0, what we're going to end up with is one point of intersection. So we can say that as long as k doesn't equal plus or minus 2, there will be one point of intersection of these two lines.